Welcome. We're going to take a look today at section 10.5, area and arc length in polar coordinates. First, we see the objectives that we're going to cover. One is to find the area of a region bounded by a polar graph. Find the points of intersection of two polar graphs, and that's trickier than you think. We'll do that in these two in the first video. The next video we will find the arc length of a polar graph, and finally find the surface area or area of a surface of revolution in polar form. Well, first let's take a peek. You may or may not remember how to find the area of a sector. Now, a sector just means it's part of a circle or a section of a circle. You could think about an orange or a grapefruit, and this would be just that a whole circle right here, and now we're looking at finding the area of that sector, or kind of a section. The area of the sector of a circle is simply given by 1/2 theta, which is the angle that this has been passed through, times r squared. So it's pretty straightforward. All I need to know is the angle measure here and that radius of the circle. So that's the formula that we'll be using in just a minute. Alright, so to find the area of a polar region, we want to consider the function given by r equals f of theta. In other words, this, you can tell the length of this from the pole is changing, and so that's my function. R equals f of theta is that distance from the pole to here. Alright, and you'll notice it's bounded. First I've got down here, this angle is theta is equal to alpha, and the upper limit, upper bound here would be theta is equal to beta, and so you can see that listed here. Okay, now how would I find the area under this curve? Well, it's not a circle like I just had, right? And just like we did earlier with shapes, you think about what we did before. We said, well, let's take, I've got some figure that looks like this. How do I find the area from A to B, right? And if you recall, we said let's make rectangles. Now those rectangles may have been inscribed, like you're going to hopefully see here. And we made a bunch of rectangles, basically of even width. This looks like it's going to be a pretty good approximation. I'm going to go a little above the curve there. And you see that. Okay, so we made these rectangles and said, let's sum them all up. And then we took the limit and said we're going to take an infinite number of these rectangles and made sure that the width of them all went to 0 as well. Same concept here, except for we're going to be looking, instead of at rectangles here, we're going to be looking at, these are going to be finding the sectors. We're going to actually add up these sectors, area of each of these sectors. Kind of a cool thing. So we first partition from alpha to beta of these, just like we broke it up with the rectangles, we're breaking it up here as well, and you see theta 1, theta 2, etc., all the way up to theta sub n, which is beta. Okay, the radius of the ith sector, so if we just pick one out here and call this one right here the ith sector, alright, it's going to be f of theta sub I. The central angle, you notice we made each of these angles to be the same, and so it's just beta minus alpha divided by n. And you can see the parallels. Earlier we did b minus a over n. The same concept, we're just using beta minus alpha because we're in polar form. That's equal to delta theta. Before we had delta x, so this is just delta theta. The area, just a reminder, of a circular sector is A equals 1/2 theta r squared. And so when I put that into place here, I'm going to see it's 1/2 is the 1/2 we've got here. My theta here we're going to actually call delta theta, because that's for any given one of these. It's simply delta theta, and times r squared, but r, remember, was f of theta, so we square that piece. Pretty straightforward. We take the limit as n goes to infinity. We get this formula, a equals limit as n goes to infinity of 1/2 times the sum as I goes from 1 to n f of theta sub I squared times delta theta, and which, if you recall what we've done before, that will morph into this nice easy formula 1/2 times integral from alpha to beta of f of theta quantity squared. And of course we're integrating with respect to theta, which is where that delta theta comes into play. So this is a formula you're going to need to know. Maybe star it, maybe think about, I have to go back to that. In fact, here's the formula right here in theorem 10.13. F is continuous and non-negative on the interval from alpha to beta. And you'll notice that beta minus alpha has to be greater than 0 and less than 2 pi. I can't go more than once around the circle to make this work, and I think if you think about it, it's really understandable why that would be the case. We get this nice simple formula. It is simply 1/2 times integral from alpha to beta of f of theta quantity squared, or if we know that r is equal to f of theta, 1/2 integral from alpha to beta of r squared d theta. So again, circle it, put something in mind to remember what that was. So let's take a peek at that. Find the area of one petal of a rose given r equals 3 cosine 3 theta. And now we've got that here. It's drawn out here on this polar graph. You can see it. And the tough part of doing these problems is to figure out where am I starting and where am I going to. If it says find the area of one petal, you can pick any one of the three. If, for example, in this problem you see one of them being shaded and it says find the area of the shaded region, then you need to find the area of that one, and I'll need to see that you understand where the endpoints are. And that, I think, really is the challenge of this problem. The integral of that, we're going to just plug it in the calculator for most likely and come up with that solution. But finding out what are my endpoints, you see it says, well, I'm going from negative pi over 6 to pi over 6. That is not really obvious that that's what we're doing. You can see the radial lines coming out, but how are you going to know that when you start? So let's take a peek at the same graph. I'm going to do it on the calculator here. And you can see I have y equals 3 cosine 3 theta, the same function. My window is from 0 to 2 pi, and this theta step is important. I went by pi divided by 24 to give myself all the options that we normally know, like pi over 6, pi over 3, pi over 2, etc., etc. I can count those out and actually know where I'm starting. Okay, so now I want to go ahead and trace this curve, and it already drew it for me. So to trace it then, I'm looking at, you can see it's starting right at this point right there. I wonder if I can, let's put this here, maybe that'll help. Yeah, I'm starting right over here. You can hopefully see that. And as I trace it, it's moving around. Well, that's too far, so let's go backwards. Oh, it's not going to let me go backwards. Let me change that just a minute. Change my window to negative 2 pi. All right, we'll graph it again. All right, we'll trace it again. All right, and so here we are. This time let's go backwards. Let's go backwards. Maybe we can go forward here. Oh, it started already at negative 2 pi. Let's go all the way around. Get back there again. And you can see this is more fun than you should really have in one day. All right. So right now, I'm at 0, where I kind of wanted to start in the first place. And if I hit the back arrow, that's pi over 24. It's 1 pi over 24, 2 pi over 24, 3 pi over 24, 4 pi over 24. So that is negative 4 pi over 24 is really negative pi over 6. And so that's how I know that I started there. And if I keep going around again, you can imagine there's 0. And we can count them again, and this is positive 4 pi over 24, which is pi over 6. So that's, I think, the trickier part of this lesson. So we took a little side jaunt over there. All right. So the area is simply now the integral from alpha to beta, which in this case negative pi over 6 to pi over 6 of my function squared. Now they used a trig identity here, and at this point in time, unless you hear differently from me, we're probably going to take this and plug it into our calculator. You'll also notice that I could have probably gone, I could have said its integral area is equal to 1/2 times 2 times the integral from 0 to pi over 6. You could have done that as well, but I would have liked to seen that. Don't just put it in your calculator, show me what you're doing. So it's not just mathemagic. Oops, there's a 3 in front there. Let me do that. Cosine 3 theta quantity squared, and don't forget the d theta. You're going to see that these two things would be equal to each other, and the only problem is you're going to get a decimal answer instead of 3 pi over 4. Okay. All right. This points of intersection, I am going to start another lesson with this, so we'll look at that in just a sec.